This is us exploring the use of Excel to do numerical modeling on some of the spiral kinematics activities. In this case, it'll be page 19, where a girl's hanging on a rope and then she exerts a burst of strength, and 2 seconds later she's traveling 1.4 meters per second. So you have already solved this algebraically, and so this is a way to check that. There's also ways that you can go ahead and use this to kind of come up with an answer that you would then be able to go back and solve it algebraically and see if you get close. So I hope to be able to show you all of that. So anyways, you'll go ahead and set up the Excel sheet with various columns, and whenever you're using a spreadsheet, you should go ahead and, I hope that didn't show up in my screencast, that you're going to put column headings with the units for each. In the future, instead of time, position, velocity, acceleration, I'll use T, R, V, and A, but then you notice the units. And also do pay attention to the fact that with acceleration, I always refer to it as meters per second per second. You won't hear me talk about meters per second squared because that's not a meaningful kind of label, but more on that later. So in spiral kinematics or spiral physics, that the important stuff to pay attention to is you should first set up a motion diagram, and I've made the assumption that the young lady started at the origin and up is positive. I identified event 1 is her starting up the rope with a burst of strength, and event 2 being her reaching her goal speed of 1.4 meters per second. And with that, that means that the initial time is 0, the initial time is 0 seconds, initial position is 0 meters, initial velocity is 0 meters per second. We don't know what the acceleration is in this problem to begin with. The next step that you need to do is to figure out what kind of time increments that you want. And this is to last for 2 seconds. And so I think somewhere in the neighborhood of, 15 to 30 data points is usually good enough. And so if this is going for 2 seconds, that means that 1/10 of a second is a good time period. So I'm going to put a 0.1 there. And then Excel allows us to be lazy, and I highlight those 2 cells. I go to the bottom right-hand corner, you notice how the cursor changes. So then I'm going to drag down till I get to 2 seconds, which I didn't quite get to. And there you have it. Okay, so some of it's off the screen, but you can live with that. I don't know what the acceleration is, but whatever the acceleration is going to be, it's going to be constant. So what I need to do is build equations that help us calculate velocities and positions. And I'm going to show you a first order numerical model on this round. Next round I'll show you a second order so that it's more accurate. But what I'm going to do is put an equation in cell C4 that talks about what my velocity would be is going to be equal to, and all equations start with an equal sign. And so my velocity in the future is equal to my velocity in the past, which is the cell right above it, plus the acceleration, which is going to be in the cell next to it, which there's not going to be anything here, but there will be in the future. And then it's going to be times the time increment. And to make things, well, to make them match with what we do with spiral kinematics, the time increment is going to always be the time at the end of the increment. So you notice I put a parenthesis there because there's an order of operations thing here that I shouldn't need to explain, I hope. So I'm going to click on that cell, and then I'm going to, so that would be T2, if you will, and from that I'm going to subtract T1. And then I'm going to hit enter. And of course it says 0 because there's no acceleration, and if I have no acceleration, my velocity is not going to change. In a similar kind of way, my position in the future, so I clicked on cell B4, is going to be equal to my position in the past, so I'll click on the cell right above it, plus the velocity that I'm traveling, and this is what will change in the second order analysis in the future one, but for now it'll be close enough. So I'll click on the cell beside it, times the time interval. So again, I will put in there T2 minus T1 and hit enter. So now I have two equations in here. So you noticed I highlighted both of those cells that had equations in them. I'm going to go to the bottom right-hand corner and drag all the way down. And needless to say, I've got zeros everywhere because if I start with zero velocity and no acceleration, I'm going to always have zero velocity. If I have zero velocity, wherever I am is where I'm going to stay. So now, if I knew what the quote answer was, if I'd gone through and calculated using algebra, I would know that the acceleration is 0.7 meters per second, and that I would have traveled 1.4 meters over that period of time. I could just plug that in and check it. So I'll plug it in. So that's 0.7. That's a constant, and in the past when I did the time stuff, that I highlighted two cells that had a pattern and then dragged it down and it repeated that pattern. In the other case, I had two equations, and so I highlighted the equations and drug those down and it copied them. In the case of a constant, I'll go ahead and just click on the cell with the constant and drag that down. And so you will notice that the velocity does end up being 1.4 meters per second at 2 seconds. And what you will notice is that if you did this by hand, that you would have gotten 1.4 meters, not 1.47 meters. But that's something that, as a first order approximation, if you're just trying to do a quick check, this is easy to do. It's a little bit more involved for the second order, not daunting, but just takes a little bit more. So anyways, that's how you do it. If I didn't know the acceleration to begin with and I wanted to kind of play around, I would just come in here and I would guess. So my first guess might be 1, and I would copy that down and check, and I would see, wait a minute, my velocity is too high. And so I'd come back and go, okay, well, let's try to bracket it. Let's make this, how about 0.5? And copy that down. And that's too low. And then I would compare and say, well, you know, it's somewhere kind of halfway in between. So maybe I'll try 0.75 and copy that down, because that's kind of halfway between 0.5 and 1. And I see I'm getting really close. So this is how you can do numeric modeling to try to catch on to whether or not things are whether your answers that you have created algebraically are close, or if you don't have any clue and you just want to have a goal to aim for, how you can experiment with it to look. Next time around, we'll do second order approximations and then show you how to create position versus time, velocity versus time, and acceleration versus time graphs. I hope you enjoyed.